Good day and welcome to today's class. Today we'll be talking about chemical kinetics. So let's dive right into it. I'd love to break the topic into two words, one chemical and the other kinetics. When you hear the word chemical, what comes to mind? I would love to say reactions. Okay, so a reaction called chemical reaction. And a chemical reaction in chemistry is simply an equation that has two sides, one side called the reactant and the other side called the product. So any reaction or any equation rather, okay, that has the product side and the reactant side is called a chemical reaction. Take for example, I have the thermal decomposition of limestone CaCO3 to produce CaO and CO2. In this reaction, CaCO3 is the reactant, while CaO and CO2 are both the products. So hence, the thermal decomposition of limestone is regarded as a chemical reaction. Okay, let's move straight to the next word, which is kinetics. Kinetics simply tells us the idea of speed. Okay, so kinetics talk about the speed of a reaction, how fast a reaction can occur. In chemistry, some reactions are fast while some are slow. Okay, take for example the reaction or the hydrolysis of sodium. When we react sodium with water, this will give us an alkali, NaOH, sodium hydroxide, and H2 gas. Balancing the reaction, we add these numbers. Also, let's also look at the reaction, the rusting of iron, the reaction between iron and water. Okay, this is going to give me Fe3O4 and H2. Balancing the reaction, we have a 4-year, we have a 4-year, and we have a 3-year. These two reactions look quite similar, right? But the thing is, even if they look similar, okay, one is faster than the other. This reaction right here is fast, sorry. While this reaction down here is a slow reaction. So they have various what? Various kinetics. So various reactions have various kinetics. That means they have different speed. Sodium and water is very, very vigorous. It can react in less than a minute, in a few seconds. But iron and water, it's almost very inert. So it takes a very long time for it to react, days, weeks, months. Okay, so do you get the idea? I believe you all get the idea now. So when you talk about chemical kinetics, we talk about the speed of a reaction. Okay, now apart from talking about speed, kinetics talks about something else. Okay, it talks about the reaction. We call it reaction mechanism, which means how a reaction occur. Don't worry, in videos to come, I'm going to talk about reaction mechanism. So for now, let us deal with speed of a reaction. So let's talk about reaction speed, or let's call it rate of reaction. So by textbook definition, rate of a reaction is simply the change or the rate of change of concentration. So you can say mathematically, the rate of a reaction is equals to the change of concentration of either the reactant or the what now, or the product, divided by time taken. So when we divide the conc of a reactant or product over time, we get the rate of that reaction. We get how fast that reaction occurs. Okay, let me give you a simple idea of what I'm trying to talk about. Okay, let's look at two boxes representing A, and this is representing what now? B. So this is a reaction A to give just a simple hypothetical reaction A to give B. So A is the reactant and B is the product. Let me assume that this box has a volume of, let's say, 1 liter. Same as this box also have the same volume of 1 liter. Okay. Now in this box we have some molecules of A, some amount of A. So how many do I have? Let me just count 1, 2, 3, 4, 5, 6. That means we have about, let's say, 6 moles of A. Now, from your knowledge in stoichiometry, we know that concentration is equals to mole or amount of substance over what? Volume. So hence, how many, what's the mole of A here? We have 6 moles of A divided by the volume of A here is 1 liter. That means that the conch of A in this box is 6 mole per liter, or I can call this 6 molar. Okay. Now, let's say the time taken at the beginning of the reaction, T is equals to 0. That means the reaction have not started. So as the reaction proceeds, as T tends to, let's say a number, let me just use T tends to T, or let's just assume that T tends to 10 seconds. So after 10 seconds, what will happen to A? Sum of A, sum of A, okay, will start to become what? B. Let me assume that it takes a total of 10 seconds for the reaction to proceed. That means at the end of 10 seconds, all of A will have become what? Will have become B. So now we're not going to have any, I believe you can see what I'm drawing. We're not going to have any molecules of A anymore. We're going to have molecules of B. And from my calculation, I can also calculate the conch of B that was formed from A. And also, what is conch? Conch is still mole over what? Volume. So what's the mole of B now that was formed from A? 1, 2, 3, 4, 5, 6. We have 6 moles of B. And what's the volume? 1 liter. This will give me 6 mole per liter. Sorry, per liter, or 6 molar. What do you notice here? You can see that the conch of A is equal to the conch of B, which means that as the conch of A reduces, the conch of B what? Increases. So at the end of the reaction, in 10 seconds, we're not going to have any amount or conch of A anymore. But conch of A will be converted to what? To B. So A is changing to B. So as A is disappearing, B is being formed. So we can calculate the rate at which A is disappearing, and we can calculate the rate at which B is being formed. Don't forget that my formula for rate is change in concentration. Rate is change in conch. I can use, if you are familiar with this concept, we know that this symbol represents concentration. So how can we rewrite this? I can rewrite the formula above as rate is equals to change in conch of A over change in time. This is the rate of A. And also the rate of B is also equals to what? Change from my formula up here. Change in conch of B over change in time. So the rate of B, R, will be equal to change in conch of B. That's final conch minus initial conch. At the beginning of the reaction, we had 0 molar of B. And at the end of the reaction, we had what? 6 molar of B. So final minus initial, that's a 6 minus 0 over, what's the change in time? That's final time minus initial time. What's the final time? 10. What's the initial time? 0. This is going to give me 6 over 10, which will give me what? 0.6. Note that the unit for concentration is molar and the unit for time is second. So that means the unit for my rate to be molar per second. So let's calculate the rate of disappearance of A. Also, change in conch over change in conch of A over change in time. That's final conch minus initial conch over change in time. The final conch of A went from 6 molar to 0. It reduced to 0. So what's the final conch here? 0. 0 minus initial conch here is 6 over, what is the final time? The final time is 10 minus, what's the initial time? 0. This will give me minus 6 over 10. So the rate of disappearance of A is equals to minus 0.6. Now note something. Note that the rate of a reaction is a positive quantity. That means that we cannot have the rate here as negative. So what do we do now? We put a negative sign here to indicate that the conch of A is actually decreasing and not increasing. So if a negative sign comes in now, what's going to happen to this sign here? This sign will become positive. So our rate of disappearance of A is equals to 0.6 molar per seconds. Now, what do you notice here? We can see now that the rate at which A is disappearing is equal to the rate at which what B is being formed. So at the particular point, the rate of A is equals to the rate of B. Okay, let me write this out, make it look good. You say the rate of disappearance of A is equals to the rate of formation of B. Okay, I just checked my time now. I think we've um, used up the time. So now in my next video, I'll be explaining more on the rate of reaction.